You know, in the world of science, sometimes the biggest questions come in the tiniest packages. Today, we're going to step into the lab and pull back the curtain on a truly powerful molecular detective, a machine that can identify almost any substance from the smallest, most elusive clues imaginable.
So how do scientists actually do it? I mean, really, how do you take some mystery substance and figure out exactly what it is? It's a question that scientists, doctors, and especially detectives have to answer all the time, and usually the stakes couldn't be higher. I mean, just think about it. An unknown powder at a crime scene? What is it? Is it dangerous? Or what about finding a fatal dose of a drug in a victim's blood? Or maybe even explosive residue from a bombing? Or the chemical signature that proves a document is a fake? In every single one of these scenarios, getting a positive ID isn't just important, it's absolutely everything.
All right, so to solve these kinds of molecular mysteries, investigators need a secret weapon. They turn to what is, really, the gold standard technique, the ultimate clue finder. It's a technology that has completely changed the game for forensic science. It's called mass spectroscopy.
So, what is mass spectrometry really? Well, at its core, it's a super powerful analytical technique. Its main job is to measure something called the mass-to-charge ratio of molecules. And by doing that, scientists can figure out the exact identity and quantity of a substance with just incredible precision. Okay, the best way to wrap your head around this, think of it like a hypersensitive molecular scale, one that can weigh individual molecules. Or, and I really like this one, think of it as a molecular fingerprinting kit, right? Just like no two people have the same fingerprint, pretty much every molecule has its own unique chemical signature, and this machine can read it loud and clear. So the big question is, how does this machine actually solve the case? You know, it might just look like a big, mysterious black box from the outside, but what's happening inside is actually pretty elegant. Let's break it down. Okay, it all comes down to 3 essential steps. Step 1 is to ionize. You take your sample and you basically zap the molecules with energy. This gives them an electrical charge. Now, they're not neutral molecules anymore, they're ions. Step 2 is to analyze. These newly formed ions get sent into a part of the machine that sorts them, usually by how heavy they are. And finally, step 3, detect. A detector at the end counts all the sorted ions and records how many of each type it sees. So remember that. Ionize, analyze, detect. Simple as that. But wait, how does that analyze step actually work? How does it sort the ions? Well, one of the coolest ways is something called a time-of-flight analyzer. And it's basically a race. Just imagine a molecular racetrack. After all the ions are created, a strong electric field gives every single one of them the exact same push forward. Ready, set, go. And you guessed it, just like in any race, the little guys are way faster. The lighter ions just zip right down this flight tube to the detector. Meanwhile, the heavier, bulkier ions lag way behind. The machine times this journey with incredible precision. We're talking nanoseconds. And since it knows exactly how long the racetrack is, that flight time lets it calculate the mass of each ion. It's kind of beautiful, right? Just brilliant physics at work. Okay, so the race is over and the ions have been detected. Now what? What does the evidence, the actual output from the machine, look like? Well, what you get is a chart, a graph. But it's not just any graph. It's a unique signature that tells the entire story of that molecule. This chart is called a mass spectrum. And this, right here, is the molecular fingerprint we were talking about earlier. It's this unique, totally reproducible pattern of peaks that acts as a definitive ID for any molecule you put in there. Let's take a look at a real example to make this super clear. What you're seeing here is the mass spectrum for acetone. Yeah, the stuff in nail polish remover. So that bottom axis, the x-axis, that's the mass-to-charge ratio, what we call m/z. And the vertical axis, the y-axis, that's just how much of each ion was detected. See that tallest peak? We just set that one to 100%, and every other peak is measured relative to it. Okay, so decoding this fingerprint is the key. Acetone's total molecular weight is 58. And look, we've got a little peak right there at MZ58. That's called the molecular ion peak. That's the whole intact molecule that survived being zapped. But here's the cool part. That initial blast also shatters some of the molecules into predictable smaller pieces. For acetone, the most common piece shows up at MZ43. That's our tallest one, the base peak. All those other little peaks, those are fragment peaks, and they all give us critical clues about the molecule's structure. It's like finding not just the suspect, but also all the tools they left behind at the crime scene. Now, it's really important to get this. Mass spec isn't just one single machine. It's more like a whole toolkit, and you gotta use the right tool for the right job. Different mysteries need different approaches.
For example, what happens when your sample isn't nice and pure? What if you've got a messy, complex mixture, like soot from a fire? Or what if the molecule you're trying to identify is absolutely massive and super fragile, like a protein? If you just zap it with the standard method, it'll shatter into a million tiny, useless pieces. So what do you do then?
Well, this is where scientists get really clever. They pair up the mass spec with another technique called chromatography. The easiest way to think of chromatography is as a pre-sorting office. It takes that messy mixture and separates it into individual, pure compounds before sending them into the mass spec one by one. You've got different flavors, like gas chromatography MS or GCMS, which is perfect for things that vaporize easily, like accelerants in an arson case. And then you've got liquid chromatography MS or LCMS, which is the go-to for those bigger, more fragile molecules like drugs or proteins.
And for those really huge, delicate molecules like proteins, scientists also have another trick up their sleeve: soft ionization. Instead of blasting the molecule to bits with a high-energy beam, these methods are much, much gentler. They basically just give the molecule a little nudge to give it a charge. The result? You can measure the mass of the entire, intact protein without completely shattering the evidence. It's a total game changer.
And honestly, that ability to analyze pretty much any kind of molecule, big or small, simple or complex, has pushed mass spectrometry way beyond just the crime lab. Its impact is, well, it's everywhere. We're talking from crime scenes all the way to hospital labs looking for cures.
Back in the crime lab, it is absolutely essential. We're talking identifying drugs and poisons in toxicology. It was famously used in the Michael Jackson case. It's what investigators use to analyze explosive residues from bombings. It can detect tiny traces of gunshot residue or paint fragments. It can even tell the difference between two black inks to prove a signature was forged. It's incredible. And the story in medicine and biology is just as mind-blowing. Mass spec is a cornerstone of a field called proteomics, which is the massive study of all our proteins. It's helping scientists discover biomarkers to detect diseases like cancer earlier than ever. It's crucial for developing new drugs, and, get this, it even helped scientists identify actual protein fragments from a 68-million-year-old T-Rex fossil. No, I'm not kidding, a T-Rex.
And you probably don't even realize it, but this technology is working to keep all of us safer every single day. It's used to detect tiny, harmful contaminants in our food and water. It can trace pollutants back to their source to catch environmental criminals. And yep, those machines at the airport screening for explosives, many of them rely on the principles of mass spectrometry.
I mean, the progress in this field is just staggering. The early machines could only handle small, simple molecules. But today, with these soft ionization techniques we talked about, scientists can analyze absolutely enormous biomolecules, things with molecular weights greater than 10,000 Daltons. That's a huge leap in capability.
So look, it is absolutely no exaggeration to say that mass spectroscopy has revolutionized pretty much every aspect of how we investigate the world around us. It is a fundamental bedrock technology that gives us concrete answers to questions that, not too long ago, were completely unanswerable.
Think about that. From just a single drop of blood, a microscopic fiber, a breath of air, we can pull out so much information. It really makes you wonder, right? With a tool this powerful, a molecular detective that can identify almost anything, what other secrets are out there, just waiting for us to uncover them next?